Good morning, students. So this is Dr.Sofia Priyadharshini, GMCT in India. So here we are discussing radar systems, chapter unit 4, right? Tracking radar. Tracking radar. So far in the first three chapters, we have seen about the different types of radars, pulse Doppler radars, MPI radars. So in pulse Doppler radars, we were trying to find what is the range of the target, right? What is the range of the target? And in MPI, we are trying to find the velocity of the target as well, right? So but if you want to know the exact position of the target, so you have to track the radar, or if you want to find the trajectory of the radar, you need a tracking of a radar. So a radar system, a radio detection and ranging a radar system which could track the trajectory of a target is called as a tracking radar. So what is a tracking radar? A tracking radar system measures the coordinates of the target and provides data which may be used to determine the target path and to predict its future position. So future position means trajectory of the target, right? So such type of radars are called as tracking radars. So in order to find exactly what is the position of the radar, so you have to find three important parameters. So from the tracking radars you can find four parameters. One is the range of the target, and you can find the elevation and azimuth angles. So this will give exact location of the target. So finding elevation and azimuth angle will give you the exact location of the target. And you can also find the Doppler frequency shift. So the main aim of tracking radars is to find the trajectory. So what will be the future position of the target? So that is the difference between the actual previous tracking radar, other radars which we have discussed, and the tracking radars, right? So the next is a simple block diagram of the actual tracking radar. So you have a tracking radar here, right? This is the entire tracking radar, and you have a target. So this target, right? So this is your target, and this is your radar system. Your radar system consists of a transmitter, a waveform generator, and you have a duplexer receiver. So here you have a signal processing unit and a main computer for detection. And here in this chapter, unit 4, we will be concentrating on the parameter estimation and tracking. So what are the parameters we are concerned about? We are concerned about four important parameters. What exactly is the range of the target, what is the azimuth angle, and what is elevation angle, and what is the Doppler frequency shift. So this unit 4 tracking radars, we are concentrating on this part of your radar system, right? So next, so look at this diagram. So if you have a tracking antenna, this is your tracking antenna. So here is your radar antenna, and this is the main beam of your antenna, right? So where is your target now? Now your target is an aircraft here. If you look at the main beam of your radar system, it looks like this. Now what is the elevation? What exactly is the axis of the beam? This is the axis of the beam. So using this type of tracking radars, you can find the location as well, you can find the motion, you can find the size. So here in this unit, we will be concentrating on the three important parameters which will give the location of this target. So we cannot exactly tell this is your main beam of the antenna, your target may be somewhere here or here and some other direction. And ultimately you have to locate the target. And in this location needs a finding of azimuth angle, elevation angle, and range. So in this lecture we will be learning about what is azimuth angle, what is elevation angle, and how do we track this radar, and how do we find the trajectory of the target systems, right, using our tracking radars. Now we are not going to concentrate on all other parameters, so we are going to concentrate only on this. So if I want to exactly track this target, this radar antenna main beam, this is the axis of the main beam. The axis of the main beam should coincide with the axis of the target. Right? Target axis and the axis of the beam should be same. So if this alignment is proper, then we say that the tracking is done. Means tracking is in process, right? So we cannot say what is the direction of arrival of the target, right? And predicting the direction of arrival and locating it and finding the future trajectory is the actual operation of your tracking radars, right? So now we'll see this is the axis of the beam, and this here at the axis of the target also would be same. Suppose if your target is somewhere here and the beam axis is here, and what will happen? The target axis and the beam axis are quite different. So we have to remove that error or that difference. So we'll be reading about this in this lecture. So now let us learn what exactly is these two angles, azimuth angle and elevation angle. So these three parameters will give you the complete location of your target, right? So look at this. Now suppose this is your target, and assume that you have your radar here, radar antenna is there. Now so if you join this two, so this will give you the range, isn't it? The range from the radar to the target. So this will give you the range, and with the x-axis, this is the elevation axis. So the angle made by this range line with the elevation angle, this will give you the elevation theta. Elevation theta. Now if you project this in xy axis and you connect this to the radar center, the angle made by the x coordinate, which is the perpendicular orthogonal coordinate to z axis, so this angle is azimuth angle. So only with this theta you cannot find what is the location. So you should know what is r, what is theta, and what is phi. So with these three parameters you can exactly locate what is the location of your target. So you can find even the trajectory, what would be the future position of this target. So angle made by the z-axis with this range axis is elevation angle, and when you project this to the other xy axis, perpendicular axis, and if you join, the angle made with the x-axis is azimuth angle. So this is elevation angle theta and this is azimuth angle phi. So there is also another representation of the same thing. So look at here. So this is north, south, east, west, and this is your target and this is your radar position. Now this is your actual range, this line, DT line, right? So this is your actual range. Now what is your elevation angle according to it? So this angle becomes, look at this figure. So this angle becomes the elevation angle. So this is a perpendicular line, and when you join and this axis, so this axis is your angle of elevation. Now what is angle of azimuth angle? So another perpendicular axis is this north pole, true north pole, the angle made by this perpendicular line with this north pole. So this will give you the azimuth angle. So with the azimuth angle, elevation angle and range, you can find what exactly is the actual position of your target. Now by knowing the position of the target, what the tracking radar must do? What the tracking radar must do. So what, see here, look at here. So we have an extra feature in tracking radar. So we have to find the angle error. What is angle error? So we have a beam will be there, and the beam axis will be there, and the target axis will be there. The difference between the beam axis, that is radiation pattern beam axis, and the target axis, so this difference is the angle error. So you have to find the angle error and use the servo motor to mechanically steer the antenna so that the angle of the target axis and the beam axis both coincide. So this is the general operation of a radar system. So this is the radar, it will have transmitter part, everything, duplexers, everything will be there. So just I have given us only the radar, and so you have to predict the angle error. So we are going to concentrate how to find this angle error. What are the different methods to find the angle error? So once you find the angle error, so you can give this output angle error estimated to a servo motor, and this servo motor will mechanically steer the antenna of the radar system so that this error is removed and you will have a perfect tracking, right? Next. So I have told you have to find the error, right? So to find that error, you can use three types of tracking methods, right? One is the sequential lobing, and the next one is conical scan, and next one is monopulse tracking. So these are the methods which are used for estimating this angle error. So before going that, we will have a just introduction of what are the different types of tracking radar. So don't get confused. So these three methods, sequential lobing, conical scan, and monopulse tracking. So these are the tracking methods which are used for estimating this angle error. And now we'll see just a overview of different types of tracking radar systems. So we have four types of tracking radar systems. The first one is a single target tracking radar, and then automatic detection and tracking radar, and phased array radar tracking, and track while scan. These are the different types of tracking. So the first one is single target. So it can only detect only one target. So look at this. So if I have only one target, this can be detected. So if I have more number of targets, this cannot be detected. But the data rate of single target detection is comparatively very high, and it uses around 10 observations per second. And the antenna beam follows the target, so it will use the same process as I have shown here. So angle error it will find, and for finding this angle error you have to use either sequential lobing, conical scan, or monopulse tracking, and then it has to be given to the servo motor, and the antenna will be steered mechanically, right? So this is about a single target tracker, STT, right? And it will have a closed loop servo system, and always it maintains the error small. So always it keeps on correcting the difference between that angle error. The angle error correction is made continuously in a closed loop, and we see that the error there would be very small. And this is used for military guided missile weapon control radar, and the main applications are tracking of aircraft, missile targets in support of military weapon and control system. So we have the next type. So only thing is we have only one target possibly detected. So look at this. This is AN-FPQ6 precision tracking radar, so which operates in C-band, and it operates C-band around 5400 megahertz to 5900 megahertz, and this is a NASA Kennedy Space Center aircraft where it has R unambiguous of 2 power 15 miles. So this is an example of a single tracking radar. And we also have the second type is automatic detection and tracking, ADT. And this type of tracking is a part of air surveillance tracking radar, and observation rates varies from few seconds to 12 seconds, and but the data rate is lower compared to single target detection. And but the advantage in automatic detection and tracking radar is it can simultaneously track hundreds to few thousands of aircrafts, right? So there in the first one only single target can be detected, but the data rate is high. But here in automatic detection and tracking radars, you can detect hundreds of thousands of aircrafts, and because of this is almost found in all civil air traffic control radars and military air surveillance radars, right? And we have the third type of tracking radar, which is a phased array radar tracking. So large number of targets can be held on track, and here electronically steered phased arrays radars So this is the technique is electronic steering of. So no physical movement of antennas will be there. The antennas and beams will be electronically steered. And these also multiple targets can be tracked on time shade basis under computer control, right? And the beam is electronically switched from one angular position to another in few microseconds, and it has got two advantages, like it is a high data rate, same as the first one, single target detection, and it can hold many targets in track like the previous one, automatic detection and tracking. So this also of course works in C-band, right? So let us have. So this is an example of mobile AN MPS 39 MOTR, right? Multiple object tracking radar for range safety and weapon safety using coherent MTI by NASA. So this kind of radars can detect a maximum of 40 objects. See here, this is an example of this mechanically, electronically steered phased array tracking radars. So this is a ship where you have a phased array radar. See here, this is one beam, this beam will be switching on time basis. So in all directions it is trying to detect the targets. So here is the ship which is sailing, and here is your radar. So at this angle it tracks some other target at this angle. So yeah, electronically the beam is steered using a software in all directions. So this is detecting something, this is detecting something, this is detecting something, and this side surface picture, high speed horizontal search. So this is another view of a phased array tracking radar. So the beam will be steered, okay, on time basis, and at different angles a multiple number of targets can be detected. So this is the importance of phased array tracking radars, right? So the last one is tracking while scan. So fourth type of tracking radars. So this type of tracking radars rapidly scan a limited angle sector to maintain tracks and simultaneous track and search, and the data rates are moderate, and they can track a number of targets, an equivalent of target, while scan is automatic detection of target. So this track while scan radar is used to rapidly scan a narrow angular sector, so usually both in azimuth and elevation, and the scanning can be performed with single scanning, narrow beam with pencil, or with two orthogonal fan vanes, right? So this is just an give you the introduction of what can be the different types of tracking radars, right? So here in this unit we will be concentrating more on how do we find the angle error. So I have told you how do we find the angular error. What is angular error? So what is angular error? The angular error means you have a beam axis and you have a target axis. The beam axis should be well aligned with the target axis. So that is the purpose of calculating the error. So you can calculate the error in terms of elevation angle or azimuth angle, and based upon that you have to make the servo motor rotate so as the antenna also will rotate. So to find the error, I have told you we have three types of methods. This is actually in our syllabus. So three types of tracking methods. One is sequential lobing, the other one is conical scan, the third one is monopulse tracking. So now we'll see the first one, sequential lobing. So how using sequential lobing you can find what would be the error. So in sequential lobing, your antenna has a beam which is switched at two different positions initially. So let me start with two positions. Suppose this is your target. Your target is here. So this is your target axis. This is your target axis, and your beam is switched to two positions, position 1 and position 2. Only one beam is used, right? And for this you can use, I'll be telling about the feeds and the type of antennas. So just try to understand now. So sequential lobing means if you have two positions, right? The lobe will be switched to two positions, and suppose see here. So the switching, suppose if this is the switching axis, and this is position 1 and this is position 2. Suppose your target is here, so if you calculate what is the received amplitude, which exact position will give the maximum amplitude? The one which is very near to the target. So position 2 will have higher amplitude compared to position 1. So what we are doing in sequential lobing, so we are using a beam from an antenna, and it is switched with different positions. Okay, so we cannot exactly, we don't know where exactly is our target. We try to switch to different position and try to predict what exactly is the target position. So initially for one dimension, that is one axis, I have given position 1, position 2. If my target is very near to position 2, the amplitude received by position 2 will be greater than position 1, right? So see here, so this diagram is amplitude and this is time, and position 1 is the thick line and position 2 is the dotted line. If you compare the amplitude as a target, where is the target? Target is very near to position 2. So that's why the amplitude of the position 2 is greater than position 1. So we can conclude that the target is very near to the position 2. So based upon that, your error can be calculated. So for a two-dimensional case, so you can go for 4 switching positions using 4 feed horns. So you take a parabolic antenna with 4 feeds, and that will give 4 positions, right? So earlier I have shown 2 positions. Suppose if it is right and left, you can go for 2 more positions, up and down. So by switching the lobe to 4 different positions using the 4 feed horns, so you can exactly track what is the trajectory of your target. You can find what is the error, and you can, based upon that error, so you can just give to the servo motor, and that servo motor will change the angle of your beam. So this is for two positions, A and B, and suppose if your target is in the middle and your lobes switching at time 1 lobe A, time 2 it is switched to lobe B, this and with this angle. So this is the center switching axis. So what is known here? This is the switching axis, right? So your target is along the switching axis. So if the target is along the switching axis, what will happen to the received signal? The two received signal at the 2 positions will be same. The amplitude remains the same. But if the target is towards the position A, the amplitude of A will be large compared to B. So using this analysis, you can find to which direction we have to rotate our antenna, right? So if the target is aligned along the switching axis, so these two beam A and beam B will have the same amplitude. Now if you take another angle, 2-dimensional, that is elevation and azimuth, 2 angles, then you can have 4 positions, that is right, left, up, down, right, left, up, down, 4 positions, right? So actually this switching will be in a circular process, like right, up, left, down, right, up, left, down. So this process will be continuously changing, and the angle error will be obtained, and based upon the angle error the servo motor can be changed. Also I'll try to explain in a very detailed way, right? So this is in a sequential lobing, this is the beam A position, this is beam B position, this is our radar, right? So you have the target here, and this is your target axis, right? So this target axis is along the axis of the switching beam. So this is axis of the switching beam, or the center of the switching beam. So this is the center, and the axis beams are squinted or switched, position A and position B. Now target axis and this beam axis and the center of the beam is same. So what will be the amplitude of the two received signals from at this position and this position? So both the amplitudes will be same. Suppose if the target is very near to the position A, so definitely the amplitude received by the beam at position A will be greater than B. So whatever I have told earlier, the same thing is this, right? And So it will be you can also use, suppose if you have to use a separate feed for the transmission, you can use 5 feed antenna as well, 5 feed horn antenna, right? So on the switching process is right up left down, right up left down, and again right. So this process will be continuously done in a sequential lobing, and it keeps on trying to find the error, and based upon the error the servo motor is changed and the antenna will track the exact target. So able to understand, right? So this is about sequential lobing, right? And you can generally you'll be using 4 horns and RF switches, and these 4 horns and RF switches can be replaced by a single feed that radiates a single beam squinted off axis, right? So here you are using 4 horns and RF switches. So instead of 4 horns you can use 4 feeds I have used in sequential lobing. So instead of that you can use a single feed that radiates a single beam which is squinted off axis. So squinted off axis means suppose if there is a parabolic antenna and you have a feed. So what will be the radiation pattern? The radiation pattern will be suppose, let me take this only. Suppose the radiation pattern is like this for an antenna, right? For using one feed. So that beam is squinted by an angle. So each beam will be having the axis, right? Beam axis will be there. So slightly from the beam axis, the axis of the beam is squinted. So instead of using 4 horn, we will be using only one single feed. 4 horns, we will be using a single feed that radiates a single beam squinted off axis. Means by an angle, the beam axis is squinted or changed by an angle. The squinted feed continuously rotate for an angular measurement in 2 dimensions. So see, we are using only 4 different directions. 4 different directions. Yes or no? So in sequential lobing, we are using 4 different directions, right? So 4 different directions here. So 4 different directions, right? You'll be using, so right, up, left, down. Suppose if the target is here, to the next approximation we are just making it accurate. Suppose if the target is in some other axis in this 360 degrees. See here only 4 positions we are covering in sequential lobing. So for that we are using 4 feeds. Suppose if the target is in some other position, the accuracy of this detection sequential lobing will be reduced. So to overcome that, we go for another type of a method called conical scan. So the main problem in sequential lobing is the angle of beam. So the beam angle is greater than the angle of error. So here some errors will be there, other angles we cannot cover, right? So whatever I have told you. So you have to use a pencil beam, and the focus is reduced and only identifies direction, but not exactly the position. So this direction, only 4 directions are well approximated in sequential lobing. And the main application of a sequential lobing is this kind of finding the error method is used in ground-based radar tracking system, right? And because of these issues only, we go for the next type of error detecting, like using conical scan. So conical scan will be using only 1 feed, and you have an antenna. So this antenna beam is squinted, right? Squinted means so see here, this is the actual beam, this is the actual beam axis. Now this is squinted in this direction, and it is rotated like this. So this is the actual beam axis. So it is squinted, changed by an angle, and it is rotated in the circular way. Now how many directions we are finding the target direction? So we are trying to find the target from all directions, isn't it? 360. So it will be continuously rotating, scanning. So that's why it is called as conical scan. So clear? Conical scan. So one of the simplest conical scan antenna is a parabola with an offset rear feed rotated about the axis of the reflector. So if the feed maintains, it is rotating like this, right? in a circular way. So it is rotating in the circular way. So if the feed maintains a plane of polarization, so electric and magnetic field of polarization, so if it is same while rotation, it is called rotating field, and this requires a flexible joint. And if the plane of polarization changes while rotating in a conical scan, so that kind of feed is called as rotating feed. So most of the time we prefer in radar tracking radars rotating feed for conical scan. So able to understand? So this is your conical scan. You have a beam. This is antenna beam. This antenna beam is squinted and it is rotated in a circular way, right? So right. So let me explain you. This is an example block diagram of a conical scan, right? So you consider it has a transmitter. So already we know second detector, receiver with AJC, duplexer. All this will give a range. Read it, same thing. So you have a transmitter and receiver session. So from the receiver session, what we have to do? You have to find the error signal, and based upon the error, you have to find the rotate the servo motors. You have two servo motors. This is your radar antenna, and this is your radiation pattern beam, right? And this will be rotating like this, conical scan by a squinted angle. Now it has to rotate and exactly find the location of the target. So there you need a servo motor which will exactly steer this antenna to minimize the error in the elevation angle as well as the azimuth angle. So for this, initially we will be giving a reference signal, two reference signal to elevation angle error detector and azimuth angle error detector. So these two reference signals, sin 2 pi FST, cos 2 pi FST. So these two are orthogonal to each other. So Fs is intermediate frequency, right? So these are orthogonal and this is given. And whatever we have estimated using a range graded error signal, that is also given to the error signal. So whatever the error in elevation and error in azimuth angle, so these two are amplified and then given to the servo motor. Earlier I have given a radar, error detection, servo motor. The same thing for conical scan in an expanded way. This is this diagram. So this elevation servo motor will rotate this antenna and change the direction of the antenna. So what we are doing here is we are trying to find the direction of the target in all the 360 degrees. So in whatever direction in accuracy compared to the first case, sequential lobing, conical scan has got better accuracy. So able to understand, right? So we have if the antenna is small, so definitely it may be easier to rotate the dish, so which is offset rather than feed. So avoiding the problem of rotatory or flexible or of joint in the feed. The same motor that provides a conical scan rotation of the antenna beam also drives a two-phase reference generator. So all this discussion is about the elevation and azimuth angle, error detection and changing the servo motors. Right? So what happens is, so your antenna, your conical scan antenna beam will be rotating like this. Suppose if this radiation pattern is of the conical scan antenna, this will be rotating like this, right, in a circular way. So suppose if your target is very near to 270 degrees. So what will happen to the amplitude? The amplitude will increase. And again if it is moving away from the target, again it will reduce. Again it will reduce. So you will have a change in the amplitude of the signal. So when your radiation pattern beam is very near to 270 degrees for this example, because your target is at 270 degrees, so you can rotate it, and with this circular rotation conical scan, so you can find the accurate exact position of your target, right? So we have third one which is monopulse tracking, so that will be discussing in the next class, right?